The moon, so close yet so hard to reach. It hangs in our sky, a constant companion, but landing there is one of the toughest challenges in space exploration. We've landed there before, so why do so many modern missions still fail? Decades after Apollo, the moon remains a formidable target for even the most advanced spacecraft. Despite advanced technology, recent robotic landers from Japan, the US, and private companies have crashed at the last moment. Each attempt brings new lessons, but also new setbacks. Landing on the moon is like parking a car blindfolded. No air for parachutes, just rockets and perfect timing. Every second counts, and there's no room for error. Even the smallest error in firing those rockets can end a mission instantly. A tiny miscalculation or a brief engine glitch can mean disaster. The moon's surface is dusty, cratered, and unpredictable, exposing the limits of our sensors. Shadows hide hazards, and the fine lunar dust can confuse even the best cameras and computers. Recent failures show that space exploration is never routine, no matter how smart our robots get. Each landing attempt is a high-stakes test of engineering and ingenuity. The real problem? We're relying on sensors with hidden weaknesses, and the moon is merciless at revealing them. Its harsh environment exposes every flaw in our technology. To land safely every time, our explorers need to see and adapt, more like humans, less like machines. Human intuition and adaptability are still unmatched by our most sophisticated robots. So, what's the solution? Let's dig deeper into the challenges and innovations that could finally make lunar landings routine. The biggest challenge for lunar landers is knowing exactly how high they are during descent. If a lander misjudges its altitude, it can crash or run out of fuel. There's no room for error. This isn't a new problem. Even Surveyor 3 in 1967 bounced after its radar altimeter was fooled by lunar rocks. Recent missions like Japan's Hakuto R and Intuitive Machines' Odysseus faced similar sensor failures, leading to rough or failed landings. These landers rely on instruments that can't double-check their own data. If the sensors are wrong, the lander blindly follows, often to disaster. We've built brilliant robots, but without real-world awareness, they're flying blind. The core issue: our landers lack the common sense to question their own readings. On the moon, that's a fatal flaw. Why do sensors like laser altimeters fail on the moon? These high-tech instruments are designed to measure distance with incredible accuracy. So what goes wrong when they're put to the test on the lunar surface? The answer lies in the moon's chaotic surface, which is far from smooth or predictable. Craters, jagged boulders, and layers of powdery dust confuse laser beams, sending mixed or misleading signals back to the lander's computer. Dust clouds kicked up by powerful landing engines can block, scatter, or even reflect the sensor's signals, making the ground seem closer or farther than it really is. Sometimes, precision sensors only activate in the final moments of descent, leaving little time to react or avoid hidden hazards beneath the dust. Robots trust their instruments completely, but a single number from a sensor can't provide the full story or context about what's really happening below. Unlike humans, robots can't see the whole picture, use intuition, or recognize subtle signs of danger until it's too late to change course. The result? Landers are often too trusting of their own senses, and the moon's unpredictable surface can easily exploit that trust, leading to risky or failed landings. The very act of landing creates new hazards, dust, debris, and shifting terrain that sensors can't always handle or anticipate. Without context or backup systems, even the best technology can be fooled by the moon's tricks. To land safely, we need a smarter, more adaptable way to sense and understand the moon's surface, one that combines technology, context, and maybe even a bit of human intuition. The Apollo mission succeeded where robots struggle because they had a human pilot in the loop, making critical decisions in real time. Astronauts could look out the window, assess danger, and take control if the computer was heading for trouble or making a mistake. Neil Armstrong famously took manual control during Apollo 11, steering away from a crater with just seconds of fuel left to spare. Apollo 12's Pete Conrad handled a radar glitch with skill and quick thinking, landing right next to Surveyor 3. The key was combining computer precision with human adaptability and intuition. Astronauts could override automation and make real-time decisions when it mattered most. Apollo's success was about seeing the bigger picture, not just trusting instruments or following procedures blindly. That human touch, that ability to adapt, made all the difference in the end. In 2025, Firefly Aerospace's Blue Ghost lander broke the cycle of failure with a bold new approach to lunar landings. For decades, landing on the moon had been a high-stakes gamble, with every mission facing the unknown. But Blue Ghost set out to change that narrative, determined to make lunar touchdowns safer and more reliable than ever before. Instead of relying only on traditional altimeters and basic sensors, Blue Ghost was equipped with an AI-powered vision system. Essentially smart electronic eyes that could interpret the lunar landscape in real time. As the lander descended, its cameras captured high-resolution images of the moon's surface, while the onboard AI rapidly analyzed these visuals, matching them to detailed preloaded maps and constantly updating its understanding of the terrain below. This gave the lander an unprecedented real-time awareness of its position, altitude, and any potential hazards, far beyond what previous missions could achieve. If the original landing site looked unsafe, the AI could instantly redirect the spacecraft to a safer spot, just like Neil Armstrong did during Apollo 11. But now, the decision was made autonomously, in a split second, without human intervention. The result was a robust, adaptable landing, one that relied on intelligence and adaptability, not just luck or last-minute heroics. Blue Ghost's vision system let it see the whole picture, integrating multiple data streams to build a complete understanding of its environment, not just a single data point. This was more than just a new sensor. It represented a new way of thinking about space exploration, where machines could perceive and react with a level of awareness once reserved for humans. The mission proved that giving robots a human-like sense of perception truly changes everything, opening the door to safer, more autonomous exploration of distant worlds. Intelligent, vision-guided landings aren't just a technological upgrade, they're the future of lunar exploration, setting the stage for a new era of discovery. The idea of combining vision with other sensors isn't new, it's how self-driving cars work on Earth. Cars use cameras, radar, and LiDAR to build a complete model of their surroundings, a process called sensor fusion. If one sensor fails, others fill in the gaps, making decisions safer and more reliable. Space engineering has been slow to adopt this approach, sticking to proven but limited tech. Recent failures have shown that relying on a single sensor is risky. Blue Ghost's hybrid system, vision plus traditional sensors, mirrors the best practices in autonomous vehicles. The vision system provides big-picture awareness, while altimeters offer precise data. Fusing this information lets the lander make smarter, safer decisions. The lesson: don't trust just one instrument, combine strengths for resilience. The space industry is finally catching up. Blue Ghost's success marks a turning point for lunar exploration. Hybrid systems, AI vision plus traditional sensors, solve the core problems that doomed earlier missions. This approach is essential for future lunar bases, mining, and science missions, where precision and reliability are critical. We can now target challenging, scientifically rich sites, confident our landers can adapt to hazards. The hybrid system opens new frontiers, making the moon's most interesting places accessible. The real lesson: technology must be smart and adaptable, not just precise. By learning from Apollo and self-driving cars, we're building resilient explorers for unpredictable worlds. The hybrid approach isn't just clever, it's a fundamental shift in space exploration. With vision and sensors working together, we can finally make the moon a true neighbor. This is a new vision for exploration.